let's provide a sketch of the graph of a rational function using everything that we know. So zeros of the function, the y-intercept, zeros of the denominator or discontinuities, and end behavior. So whenever we start graphing rational functions, if we are interested in the zeros of the numerator and the denominator, then our best method of proceeding is to factor. So I think I can factor this first quadratic as 7 and 3. No, 7 and 4. So let's do x minus 7, x plus 4. This factor right there, it's 12. It's got to be 3 and 4. And it's down 4, up 3. Okay, double check me that that is a correct factorization of that numerator. All right, let's factor the denominator. First factor has an x squared in common. So we can pull out an x squared. We're left with an x minus 7. Second factor, I believe factors maybe 16. So 1 and 16, no. 2 and 8, no. 4 and 4 would do it though. X minus 4 and another x minus 4. Okay. So are any of these, in fact, let's first talk about our domain. The domain is going to be all real numbers except what's going to make me divide by 0? 0 would, 7 would, and 4 would. Okay. So can we simplify R of x? Can we remove any of these discontinuities? The x minus 7 can cancel. The x minus 4 can cancel with one of them down there. I'm left with an x plus 4, x plus 3 in my numerator, and an x squared times an x minus 4 in my denominator. Let's work from this simplified version. So I do have non-removable discontinuities at 0 and at 4. So I'm going to put that on my graph as vertical asymptotes. I am not allowed to cross these vertical lines. All right, my function does not exist there. Okay, now my numerator, I can look at that and figure out where my zeros are of this function. All right, what's going to make R of x equal to 0? It's when your numerator is equal to 0. So your numerator is going to be 0 at minus 4 and minus 3. So here's a 0 at minus 4. Here's a 0 at minus 3. Okay. Let's see, what else can we talk about? Y-intercept, there is no y-intercept because we have a vertical asymptote there. Our function does not exist when x is equal to 0. All right, now I think it's time we give ourselves a test value. So let's evaluate this function at 1. And you can use the original form, but I don't know why you would. I would use the simplified version. So if I plugged 1 into this function, I'd get a 5 in the first factor, a 4 in the next, a 1 squared is 1, and a minus 3 for the x minus 4 factor. This is going to give us 20 minus 20 thirds. So that's almost minus 7. So when x is equal to 1, we're almost minus 7. I've got a point right there. All right, so starting at that point, let's draw the function, and you're going to notice that you're forced to do the correct thing. So if I put my pencil at that point and I move in this direction to the right, then I'm not allowed to increase because I know that as I approach this vertical asymptote right here, I need to either increase without bound or I need to decrease without bound. And I can't increase that without bound because then that would give myself a 0. But I know that these are my only two zeros. So if I can't go up, then I have to go down. So our function is going to do something like this. Now, as I move in that direction from my point, again, for the same reason, I have to go down. Right? I can't cross that vertical asymptote, and I can't go up, else I would give myself another 0. Okay, now let's think about this vertical asymptote right there. That vertical asymptote is a consequence of this division by x squared, right? We knew that we had a vertical asymptote at 0 because that x squared is a 0 of the denominator at x is equal to 0, and it has even multiplicity. So because it has even multiplicity, I'm going to do the same thing on either side of the vertical asymptote. If I go down to minus infinity on the right-hand side, then I'm going to go down to minus infinity on the left-hand side as well. Right? Just like if you had even multiplicity of a polynomial 0, you do the same thing on either side of it. So here on that vertical asymptote, because it has even multiplicity, I do minus infinity on both sides. All right, so I come up here, I hit that 0, and do I hit that 0 and bounce back, or do I pass through? That 0 is a consequence of this x plus 3 term, and it has odd multiplicity, so I do pass through. And then I will hit that 0 at minus 4, a consequence of this x plus 4 factor, which has odd multiplicity, so I will again pass through. Okay, let's talk about what's happening on the other side of this asymptote. This asymptote at 4 is a consequence of this x minus 4 factor in our denominator. It has odd multiplicity, so I do opposite things. So if I go towards minus infinity on the left-hand side, then I'm going to go towards positive infinity on the right-hand side. All right, last thing to talk about is end behavior. So let me get rid of some of this work and write down the original simplified function. So once we simplified, it was x plus 4, x plus 3 over x squared times an x minus 4. So for the end behavior of polynomials, sorry, the end behavior of rational functions, just like for polynomials, is dependent upon the degree. So I have a second degree here in my numerator. I have a third degree in my denominator. So my denominator is more powerful than the numerator. This denominator is going to grow a lot faster than this numerator. So this function is going to get dragged down to 0. In fact, if you were to perform this division, you would get 0, right? 0 plus some remainder. So this function is going to get dragged down to 0 for large x values. In fact, let's plot that horizontal asymptote with a blue line. Right, this is your end behavior. You need to approach this line. Now, we know that we actually never do cross it as we go infinitely to the right, because these two places are the only places that we cross. Right? You can cross a horizontal asymptote. So from this direction, I also need to go up like this. Right? I know I need to end up on that blue line. All right, so that's a pretty decent sketch of this rational function.